Talking about today is velocity graphs. And it is an abstract concept that is going to force you to think. Now, I'm going to walk you through it gracefully, I hope. And so by the end of today's session, we'll have some new formulas. Just to reinforce, I want to keep the last 4 rows of each section empty, and hopefully that'll make the iClicker reception a little bit stronger for everybody. We won't get any missing clicks. And we'll see. And you know what? Normally we keep the last 4 rows empty on exam days anyway. So this is almost like exam mode. I might even move everybody 1 more row forward on exam day. And there's reasons for that. Not having to do with clickers though. Anyway, last time we were talking about Galileo and motion. And Galileo's idea concerning science itself, he wrote a famous book, controversial book about comets. And he said that he was convinced that the universe itself was like a book that you could read if you knew the language. And his conviction was that it was written in mathematical language. And the program of study that he developed is called science, physical science. So not like a court of law, not like any other endeavor, but an endeavor unique to nature itself. So his conviction was that anything, if you're trying to say something scientific, it's going to be mathematical as well as, Italian or English or whatever language, your natural language you're writing in. And it is going to be based on observations and measurements. And it may seem like, yeah, of course, Dr. B, if it's science, but people in those days, they had, it's like I was saying, a different criterion of truth. For Aristotle, Aristotle was a relatively scientific guy. He did a lot of study and a lot of thinking. But by the time Galileo's day came, the disciples of Aristotle, they weren't really looking at nature. They were looking at Aristotle's books. And if Aristotle said it, that was it, baby. Issue over. What is that phrase they use now? It's settled science. If Aristotle said it. And Galileo said, dude, haven't you ever looked at the stars? Haven't you ever looked at something that you drop from a bridge or from the top of the library or, from the top of the Leaning Tower of Pisa? He said, no. If you're talking about the natural world, you're going to notice patterns, but you won't notice any patterns, any mathematical patterns, unless you make observations and measurements. You can't just blab. No, he was going against, and the interesting thing about Galileo is he was educated by Aristotle's school of thought. Aristotle was 2,000 years before, but Galileo, he was in the school of Aristotle until he broke free of it, and this is one of the signs of it. And my comment to you is, every single person in here, now that you're in this science class with me and you're starting to think like scientists, you're in his school. You're a student of Galileo. And of course, his #1 student was Sir Isaac Newton. Another thing that we talked about last time was how you actually calculate a distance and an elapsed time from x coordinates of positions A and B or events A and B, and from clock readings at those positions. And we're going to talk some more about that today. We used the definition of speed to actually calculate a speed, and you guys did a little bit of homework based on that. And just so you know, I had a student come up and ask me about the homework. The normal procedure for homework in this class is to have it be due at the next lecture, so 12:01 p.m., whatever the next lecture is, a Tuesday or a Thursday lecture. And also, the standard procedure is to have 4 attempts. And sometimes, if I want you to, if students want to, like if we have a fancy calculation that requires a lot of decision making and that you and your study group are working hard on, sometimes I'll let you take 6 attempts. Sometimes they'll even replicate the assignment and let you, crank on it again. And usually that happens the day or the period of time before an exam. Students are, Dr. B, can we just have another few runs on that one acceleration problem? Just so we can, because students will do that and just, get it honed to a fine edge where they can just crush it. So sometimes I'll do that, but usually a minimum of 4. And my normal time setting is 45 minutes. Now, I don't think you needed 45 minutes for homework 1, but that's just my default, that's my mental default setting. So, so that's good. Let's review one of the homework assignments. This particular unfortunate event guy, here's the, you were to calculate a distance, multiple choice, and then calculation, actually calculate a speed. By the way, when you're doing iClickers and when you're doing web courses, calculations, you have to, if you have a decimal fraction, a decimal number that's between 0 and 1, so like 0.703, don't type in 0.703. Type 0.703, all right? Now, in some textbooks, like probability class, they permit you to type in 0.703, but web courses will choke. It won't read it properly, and iClicker will choke. It won't read it properly. It won't even, I don't think you can even do it on iClicker. It always assumes a digit before you get to use the decimal point, so just keep that in mind. All right, here are the specs for this event. Go ahead and make a sketch. And let's just go over this. And I'm going to go over it with you, and you can add this to your notes, and as a second. I'm really getting tired of this. Somebody from Fort Lauderdale. Yeah, so just add this to your notes. First 4 rows empty, please. Move forward. Move forward. All right, so you have 2 events. One of them is at position negative 2.45 meters, which, and I measured this out really carefully with pixels, in my presentation software. Event number 2 is at 0.0 meters. So here's the displacement, delta x, from event 1 to event 2. And that arrow is, as long as it's an arrow, it's directed to the right. It's not a velocity, but you can call it a displacement. It has a direction that you're displacing your position. And it's exactly proportional. In fact, it's equal to the distance on this distance scale that I've written. All right. Now, another thing I want to make clear to you is that the normal order of calculating a delta x, here's the picture of it. Right? The normal method of calculating it is later minus earlier. Final minus initial. You know, so if it's positions, it's the later position minus the earlier position. The final position minus the initial position. If it's times, you know, like in elapsed time, it's the final clock measurement minus the initial clock measurement, whatever that happens to be. Now, if you have a stopwatch, the stopwatch does that for you. I mean, so, but if you're just looking at your, you know, like a wristwatch or something like that, that's how you do it. All right, so here's our delta x for this exercise. And hey, you guys, when you're doing those calculation problems, they change with at least one random number every attempt. So, so you might have had points, I think T2 is the one that changed on this problem. So you might have had T2 equals 0.74, or you might, actually, yeah, I think it was T2, and or you might have had 0.67 or something like, you know, and if you did it 4 times, you might have had 4 different T2 values. All right, so just a word to the wise, be alert to that. You cannot recycle calculation results. I mean, you can make notes on them, and you might get lucky and get the same number again, but probably that won't happen. So just keep that in mind. So here's the calculation of delta x. Later minus earlier, so x2 minus x1. Later position is 0.00 meters. The origin of the coordinates for x, subtract, and then subtract the x coordinate of the earlier event, x1, and that's a negative 2.45 meters, according to that problem. All right, now if we're measuring something else, you might have a different x coordinate. All right, but if, you know, but whatever you have, you subtract it. All right, so subtraction of a negative is the same as addition of a positive. So 0 minus a negative 2.45 meters is the same as 0 plus regular 2.45 meters. So delta x is 2.45 meters. All right? And hopefully you didn't get tripped up on that. Delta t is similar. You go with the T2 and the T1, and it's T2 minus T1. Earlier clock measurement minus, or excuse me, later clock measurement minus earlier clock measurement, whatever it happens to be. So this one is 0.74 seconds minus 0.00 seconds. So this one's a little easier, right? So the elapsed time, delta t, or the time increment through which this displacement occurs is 0.74 seconds. Now to get the speed from those two sub-calculations, you have to make the quotient. So V equals delta x over delta t. And numerically speaking, that would be 2.45 meters divided by 0.74 seconds, and that works out to 3.31 meters per second. Go ahead and verify that on your get your calculators out and re-verify that. And I'll just make a note here to you that you can look at page 10 and see an example of that. Okay. Now let me pause for questions before we continue. Go ahead.
For velocity, are we supposed to write down the direction?
In general, yes, but on this one, we're only working on the x-axis. Okay, so that's one dimension. So the direction is only going to be either to the left or to the right, right? And this is a good point. How do you represent a direction left or a direction right for a problem like this? The way that you would do it is by using a minus sign to represent leftward, and a positive sign, which is what we've got here, to represent rightward. All right? And so occasionally that will be necessary, like when we start doing free fall. But on this one, it turns out to be positive. But if we'd done the reverse motion, if x2 had been negative 2.45 and 0.00 or at, well, no, you'd have to do, 0.00 seconds and 0.00 meters, then you'd have a leftward motion, and you'd come up with a negative sign in there. Okay, so, and we'll do some examples where that brings it out. Okay, another question. Yes.
For one of the homework questions, it was asking if it was accelerating north, like which direction it was going.
The Oviedo chicken.
Yeah.
Yeah.
But it showed with arrows, and it was accelerating north, but the answer was the arrow going south. But I didn't get like that.
That I thought I corrected that. Are you saying that the wrong?
Yeah, the answer was saying that it was going.
I thought I corrected that. It was in the test bank. Oh man. I tell you what. I thought I corrected that before I assigned it to you guys.
We can all get an extra point.
That
We could all get an extra point for it.
yeah, technically yes, that's true. But why would I want to do that? No, I think I'll figure something out. See, the problem is that there's 200 of you with it. And the problem is sometimes when the web canvas, when you export, the calculations weren't working at all. They actually, if you write a calculation problem, it exports from one course to the next course, or from one course to a zip file is what it exports to. It turns every calculation problem with a formula into an essay problem. What? An essay problem? And so there's all kinds of little things. But I thought I got that one that you're mentioning. But I'll try to rectify it. I might give you the problem again just for bonus or something like that. Question in the back. And by the way, there really are chickens in Oviedo. Is there anybody here from Oviedo? So you know that there's chickens. All over the place in Oviedo. Chickens, they just roam the streets at random. Okay, question. We're going to go over it. That was a challenge problem. And we're going to go over it either at the end of class today or first thing on Tuesday next week. Okay. Because it's about acceleration. Okay. But actually, you know what it's like? It's a lot like this. Except that you're working with velocities, not displacements. So, but we'll get to that hopefully by the end of class today. Okay. All right, so let's just go through this again here. All right, prepare yourself for some eye clicking. Press and hold the power. If you haven't used your eye clicker before yet, press and hold the power button until the letters flash in the upper left. And then type in the frequency DD, and you'll get a Go Nitro message. And Dare, this is this is numeric. Okay. Then you get the ready message. Okay. Raise your hand if you got a Go Nitro. Nice. All right, now this is the first day of class participation, so this is a real question. So do your best with it. It's a calculation. And this is a calculation like the one that we just did together. All right, so let's see if you guys can crush it. All right, here you go. Two different events. Event U and J. Hold on. We're having a hard time getting this thing.
The mouse is freaking out.
Oh, you know what it is? It's because both of these things are...
Wanting to locate back up there. Oh. Okay.
All right, go ahead. You should have It should let you type in an answer now. Yeah, what does the time tell you? Time tells you which one's later. 3.2 seconds versus 4.6 seconds. What are those batteries doing up here? Is that your phone? No, that's not a phone. That's the this.
Oh no, that's the base.
That's the base.
Desktop. Okay.
All right, now type it into two decimal points.
Okay. That's
The nearest hundredth. Yeah, I have no idea. You know what happened? If I'm like eating Cheetos or something, and I'm trying to operate my clicker or my mouse or something or my trackpad, the Cheeto molecules interfere with the trackpad. Did you ever notice? You don't eat Cheetos a lot. Okay. If you ever eat Cheetos, it's... Dude, I'm recording this. What? No, just type in the numeric part. So a number. Just give me a number. You know, something point something something. Right? And then hit the send key. Because it doesn't know. You know, Darius having a hard time up here, but you guys are doing good.
This is not happy.
See if you could just use the...
I was trying to use that one and it was doing the same thing.
Something else is...
Yeah, it might be like one of the wires or something is weird.
Yeah, we're having a hard time.
Is this a touch screen? This is a touch screen, right?
Yeah, see if you can...
Maybe
All right,
there's-
let's do a countdown.
I wonder if there's something up here that it's pressing.
Possibly.
Because that's what it looks like. It looks like something keeps touching it.
I wonder if it's a wire. Has anybody got a wireless mouse that's butt dialing this computer? That's what this looks like. If you're doing it, I'm going to track you down like Chinatown, hopefully. And this, all right, see if you can do it by digital. Okay, countdown. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Don't use the mouse. Use your hand. Sweet. All right, see if the menu will work, the drop down.
That's
No.
not wanting to work.
All right, we're going to have to fight this
Yeah.
2 more times.
Are the other two multiple choice?
What's that?
Are the next two
Yeah.
multiple?
1.02, most of you got that. Very good, 80% of you. I see somebody with 1.04, negatory. That's a little bit, it's a poor round off. Somebody typed in 1, negatory, that's too much round off. Anyway, let's keep going. I want to talk about this new topic today, average velocity and instantaneous velocity. And this will actually help you understand the Oviedo chicken principles that you were challenged on with homework. By the way, we'll have some homework this weekend, and I might put the Oviedo chicken problems back in there, make up for this disaster. So let's talk about average and instantaneous velocity. Okay, average velocity or average speed is based on a finite number of position and time measurements, and so that you get, add them up and divide by 2, or just, a delta x and a delta t. And so you're basically working with events or two snapshots in time, like this one that we've already talked about from homework number 1. Now, my concepts to you this afternoon is this. If all you know is position and time at two different events, pictured here with the stick figure, you don't really know what that guy's doing between t equals 0 and t equals 0.74 seconds. Okay? He might have been the same speed the whole way through, just like the hare. No, just like the tortoise. Or he could have taken a break and then sped up again like the hare in the tortoise and the hare example. So definitely look at chapter 1-11 and review that stuff. You can also read about the Turkey Lake Service Plus. I think there's an example in there about that as well. They're dashing towards something. Now, the tortoise and the hare fable, we'll continue talking about that. That encapsulates the difference in the two concepts. It's based on two dynamical ideas. But one of them is that the tortoise, once he gets going, his speed at any instance of time is the same as what it has been for the entire time he's going, and that's going to be his average speed. Right now, I mapped that out for you in this diagram in the e-textbook. All right, now and it's just nice and smooth. The same, it's not very fast. Those blue rectangles, they're not very high up on the speed table, but they are what they are. And the tortoise, he wins the race. Now the hare's velocity state, slightly different dynamical concept here. His velocity state changes several times during the race, and that's why he loses the race. The famous tale. So I just kind of made up an example. He's going certain speeds, he slows down. So this one, for the hare, the rectangles, those blue rectangles up there, they're different sizes. Some of them are taller than the others. And then there's a whole bunch of zeros. And that's where you don't see any rectangle at all. He's at rest. And so when he's at rest, he's taking a snooze. And while you snooze, you lose. If you're heading, if you're going up against the tortoise. Because the tortoise, he's just cruising. He's just, he's, all right, I'm not that fast, but at least I'm keeping going. And he wins the donuts or whatever it is they're fighting, they're competing for. Now, in terms of instantaneous speed, the velocity is a function of time. You pronounce v of t, you write it v and then parentheses t instead of the parentheses. That's a constant for the tortoise. But v of t is all over the place for the hare, right? And it's possible for it to be all over the place for the hare, and the hare wins. But in the fable, the tortoise wins and the hare loses out. So this idea of velocity or speed being a function of time, possibly different values at different instants of time, it's encoded in these two diagrams. And sometimes there are patterns. Matter of fact, we've got a pattern for the tortoise. The tortoise's pattern is ditto marks all the way across. 1 meter per second, 1 meter per second, 1 meter per second, 1 meter per second, all the way across until he wins. All right? There's no pattern for the hare on this one. All right? So this particular graph, this is a velocity graph or speed graph, and there's something really useful about this. Go ahead and make a note of it. This is what's useful. It's nearly rectangular. Now this is an abstract graph. It's not a diagram. All right? It's not like you're not on graph paper with X and Y coordinates. Your vertical axis is a speed rating. So you know what this is like? It's like an EKG. You know, an EKG measures I think it measures your blood pressure it measures the voltage in your heart. So the vertical, it goes up when your heart pulses a little bit of an electrical pulse, and then back down to zero when your heart's not pulsing out electricity. So this is a little bit like that. It's kind of abstract. But what we're going to do is start studying this abstract idea. And the first graph that we're going to study is constant velocity versus time. Right now, we already looked at the hare and the tortoise, and the tortoise was pretty close to constant velocity. Now let's completely modify the graph to be perfectly constant velocity. So here we go. Right, this is the most basic velocity versus time graph there is. Vertical axis represents velocity. So a plus value, positive, means in this graph, and I want you to add this to your notes. In this graph, it means you're moving to the right. And a negative sign, you know, there's a question somewhere from somebody, you know, well, how do you deal with directions? A negative number signifies, or on the vertical axis anyways, negative numbers on the vertical axis signify that you're moving to the left. All right. Now this graph, the dotted line, represents, you know, somebody like the hare, or excuse me, somebody like the tortoise that's moving at a straight, steady, even 1 meter per second rightward. All right. Now the horizontal axis represents time, and you can see that in here. And this particular graph that I've sketched, and I'd like you to sketch, shows the object moving from t equals 0.0 seconds out to 2.5 seconds, 2.5 seconds. You know, and the guys at NASA that are trying to put a spacecraft into orbit, they'll do really small increments of time, you know, milliseconds. But they do similar stuff. And actually, everything that we do today is related to stuff that they do at NASA when they're figuring out. If you ever saw that movie, Hidden Figures, raise your hand if you saw that movie, Hidden Figures. Oh my goodness, one of my favorite of all movies. Wonderful. You know what? You should, if you have Netflix, I don't know if it's on Netflix, but if you don't have, if you haven't seen it, go try to see it. You know, borrow it or you know, check it out at the library or something. It's related to what we're talking about today, and for the next few days. All right. So our graph shows an object moving at 1 meter per second to the right for about 2.5 seconds. All right. Now, this is really boring. It's the tortoise type graph. But we're going to look at it because, you know, constant velocity, 1 meter per second rightward, 2.5 seconds worth. It's kind of boring, but it's going to be our entry point for something that's going to be extremely useful and definitely not boring. All right, so the graph is, so when I say the graph, that's the dotted line. All right, and just so you know, this is similar to the tortoise's graph. And this particular graph, it's represented as a dashed line, but it basically encodes the instantaneous velocity at any instant of time. All right, so all the instants of time, at least visually, you can make a list, You could make a list, but you'd still have finite increments of time between all your velocity readings, and that's what I do in the textbook. Now, this one's all smooth and nice, and visually, all instants of time are encoded by that horizontal smooth line. All right. Now, what I want you to do next is, with this graph, I want you to shade in the rectangle between the graph itself and the time axis. All right, so that's like this part. Right, shade that in. All right. So just dip down from the end of the graph down to the time axis, and then kind of shade it in gracefully. All right. And as I've mentioned, the straight line represents its velocity pretty nicely. But what does the enclosed rectangle represent? It's on the graph. It has a physical meaning. It's abstract, but you know, what does it, does it have a meaning? All right? And so what we're going to do is look at the area of this. I mean, it's a rectangle, right? So the area, go ahead and write this down. You know this from like 7th grade. Area of a rectangle, base times height. Length times width. All right? And so this is a real cinchy area calculation. Nothing fancy about it. And so let me park this up on top here. Now let's put the numbers in that we have for the base and for the height. The base is 2.5 seconds. It's not a distance, it's a time increment. So the vertical height is not a distance either. It's an increment of speed. All right? So length or base times height is 2.5 seconds times 1 meter per second. All right? Now, I want you to pause and think about that and just make a note, a mental note in your mind that this is abstract. You know, in geometry class in 7th grade or 10th grade, whatever semester or whatever year you had geometry class, that was talking about regular figures that you could graph out on graph paper. This is not that. On graph paper, you have inches left and right, and you have inches up and down, you know, or centimeters left and right, and centimeters up and down. So the product of two measurements, a length times a width, a base times a height, on graph paper is going to be, you know, so many square inches, or so many square centimeters, or so many square light years, or whatever, you know, the distance units that you're using. But not here. Now, so make it emphasis to yourself. This is abstract. It's not it's something you can put on graph paper, but it's not something that you can photograph. Okay? You know, you can photograph a trajectory on graph paper. You can walk a trajectory on graph. You can't really, you know, this is not something that you can walk or photograph or anything like that. So it's abstract. Let me ask you a question. Look at that. Look at this equation here in the middle. Get my cursor over here. Come on, cursor. There we go. Look at this equation over here. Notice anything interesting about that? Anything catch your eye? You're going to see it in a second. What do you see? See anything? Look at the right-hand side of that equation. I mean, the left-hand side just says area and then equal sign. What about the right-hand side? You see anything? What do you see something? What?
1 meters per second instead of just 1 meter.
No, it's supposed to be 1 meter per second because it's a speed. This is a velocity graph, a speed graph. All right? But just look at the, what do you see?
That number is going to be something 2.5 meters per second squared.
No, not meters per second squared. You're getting warm though. Look at that. What do you see? Seconds can cancel. This second's over here in the second part of the right-hand side. It's in the denominator. Is that what you're kind of thinking of?
Yes.
Yeah. But this one is in the upstairs. It's in the numerator. So guess what? Ching! Go ahead and cancel those babies out. Now, you can't cancel the meters. All right? But that's all right. 2.5 meters. And let me just ask you, if you're moving at 1 meter per second for 2.5 seconds, how many meters have you traveled? 1 meter per second for 2.5 seconds? 2.5 meters. So this area, you can actually interpret the area that you've shaded in as the distance traveled, right? Now this is an abstract result. It's on an abstract graph, but it is 100% kosher. All right? So whenever we have a velocity graph, if we make, vertical lines left and right, and then stop at the time axis, and then shade it in and figure out the area, that'll be how far we move. And guess what, students? That will hold for the hare's velocity graph as well. Because the hare's velocity graph from the textbook is just a bunch of rectangles. So just count up each rectangle, measure it up, and then add them all together, and that's how far the tortoise goes, or that's how far the hare goes before he takes his nap. Right? So all of this stuff perfectly jibes with this formula. Delta x equals v delta t. All right? Distance equals speed times time. You may remember that from, like 10th grade science class or something. Distance is speed times time. And hey, you guys, distance delta x, v is the height. All right, that's the height of the rectangle. Delta t is the base of the rectangle. So yeah, this is all kosher. That formula that you may have learned in 7th grade or 10th grade or something like that, distance equals speed times time, the equation that you know in your head without even having to think, you're driving, to Miami at 65 miles an hour, let's see that, and I got to go 130 miles, so that's going to take me 2 hours, so you just kind of mentally do that all the time when you're driving, at least I do. Yeah, it's all consistent, and it's actually related to a velocity graph. Now, I'm going to give you a mental IQ test question. All right, and I want you to think. All right, I want you to look at this diagram of dots. Each one represents a snapshot of a position. In the sequence A, B, C, D, E, lapse time of 0.1 seconds between. So this is like a strobe photo. You know how strobe photo, you see, like a bird flying, stop motion, and you see, several images of the bird or whatever it is that's moving. So look at that and ask yourself, which of the 4 options describe that image of dot A, dot B, dot C, dot D, and dot E? All right, go ahead and vote for that. And remember, you want to try to get every answer answered, and you want it to get correct. Oh, you know what? I forgot to tell you to hit the refresh key. Because we changed from numeric to multiple choice. Hit the refresh key. Doggone it, I forgot to do that. Hit refresh key, and then you should be able to type in A, B, C, D, or E. Okay. Hit the refresh key. Okay, type in a letter.
But press one of the like letter buttons.
The letter buttons. Yes. Yeah, you can change it if you want. Remember that the iClicker software remembers the very first thing you send and the very last thing you send. So if you send 7 answers, you change your mind seven times, it'll remember the first thing you sent and then the very last thing, and it won't forget the interior 5. All right. All right, good. 10 seconds to get in a click. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, good. This one is actually slowing down. Most of you got that, 57%. Now, if you were one of the people that voted outside of option B, make a note to sketch the dots exactly the way I've got them. They're very carefully measured and laid out. The distance between A and B is big. The distance between D and E is the smallest. But the time increment between two adjacent dots is 0.1 second, a tenth of a second, right? So for the distance between A and B, that's your big distance, tenth of a second. So it's going fairly good speed. Between dots D and E, it's going a little teeny distance, same amount of time, 0.1 second. So it's going kind of pokey. So it's slowing down, right? Now, let's attack the velocity graph for something like this strobe photo, something that is slowing down. And this is where it's going to get interesting. The first velocity graph we just did, base times height, boring, it's the tortoise. But now we got something that's accelerating. So let's talk about the concept of acceleration, and then we'll do a velocity graph for something that's accelerating. The idea of acceleration is how fast is the velocity changing, whether slowing down or speeding up or changing direction in a certain elapsed time. So it's always a ratio, delta V over delta T. All right, now this is getting towards the Oviedo chicken thing. All right, delta V is the later minus earlier. So if the Oviedo chicken is faster afterwards and slower beforehand, that means big minus little, positive number, therefore a rightward arrow. All right, so this is how that Oviedo chicken problem works. All right, but this is a formula, and that's graphical. Now, if you have a known acceleration, you can use it to figure out a distance. Acceleration times time. Or excuse me, you can use it to figure out a change in the velocity. All right, so if you know that something is, for every second of free fall, you're getting 9.8 meters per second of downward speed, and you fall for 2 seconds of free fall, that's a total of 19.6 seconds. No problem. All right, and we're going to be talking about free fall on Tuesday. All right, so these are the two formulas that we want to talk about. And now we're going to go and talk about another velocity graph that I like to call the distance triangle. Here it is. Right? Now this is a velocity graph for something that's slowing down. Okay, Alex? It starts with a bigger speed, 3 meters per second, but in 4 seconds of elapsed time, it slows down, and after 4 seconds, it stopped. How do I know it stopped? Because the graph ends at 4 seconds on the time axis. And on the time axis, in this graph anyways, it means that you have 0, you're stopped. Okay? The time axis is between the positives and the negatives. Right? So this one's, it's moving to the right, but it's slowing down. It's kind of slowing down and getting easy and just kind of poking along. All right? So this, it starts at rightward 3 meters per second, but then it comes to a stop at 4 seconds. V equals 0.0 meters per second. All right? Now, again, I want you to shade in the geometric figure between the velocity graph and the time axis. That means it's a triangle. All right? So this is the distance triangle. And as before, the interpretation of this area is the distance traveled, not by something that's at constant speed like before, but something that's changing speed. We could still use the area interpretation as the distance. All right? So let's look at this distance triangle. Here it is. Top value is 3, bottom value is 0. Sideways it goes from 0 to 4. Anybody remember the area formula for a triangle? 1/2, that's right, 1/2 base times height. Now that's for any triangle. If it's a right triangle, if it's obtuse triangle, you know, the altitude is different looking for an obtuse triangle, but it's, you know, same as this one basically. All right, so 1/2 base times height. And you know why that 1/2 is in there? Because it's the same as a rectangle, except you're cutting it in half. You cut across the diagonal, slice across it diagonally, you throw away the other half. You don't want that. You just want the triangle. So it's half of whatever your rectangle was. Base times height, and you just take half of it for a triangle. All right? Now, go ahead and write in a 1/2 and then parentheses for the base. Okay? In parentheses, what is the size of the base? Write that down in parentheses in your notes. Okay? And then another set of parentheses, the height. Write down, according to this graph, what should the height parentheses have inside of it? All right? Now, is this what you have? 4 seconds for the base, 3 meters per second for the height. Do you have that? Raise your hand if you have that. Good. All right, the rest of you guys, type that in. Now, I'm going to do a little bit of rearranging the furniture here. That 1/2 out in front, I'm going to park it underneath this 3 meters per second. Right? And I'm going to draw your attention to that particular quotient because it has a meaning as well. This quantity does have a name. It's the average speed. You know, if you know the speed at the beginning and the speed at the end, and then add them up and divide by 2, that's the average. Right? That's one way to calculate the average. Right? So if you add up 3 to start with, and then 0 to finish with, and then divide by 2, it's 3 meters per second divided by 2. Right? So this part of the equation is actually an average speed. Now, average speed times elapsed time is a distance. You know, the seconds cancel out again. And this is what we have, delta t times average speed. So another thing that I want to point out to you for that average speed, the average speed, the change in the velocity is also a delta t. You know, the change in the height of the graph from 3 down to 0, that's a result of an acceleration over time. So that 3 meters per second divided by 2 can also be interpreted this way. A delta t over 2, right? And now let me push this up here. So the distance now is delta t times a delta t over 2. Right? And that's my triangle formula, or my distance triangle formula for an accelerated object. Now look at that. I've got 2 delta t's in there, and they're multiplied. So I may as well call that delta t quantity squared. And I'm going to put my 1/2 out in front again now. And here's the simplified version of that formula. D equals 1/2 AT squared. The distance triangle formula for something that's speeding up or slowing down. Speeding up, you get a triangle. Slowing down, you get a triangle. Constant speed, you get a rectangle. So sometimes you have a combination, you know, depending on the motion, you know, depending on what the rabbit is doing, you know, you might get some triangles and you might get some rectangles of various heights and stuff. But for a distance triangle, 1/2 AT squared. All right? And in general, so here's another version of it. Okay, so that's the compact version. So instead of delta t, I'm writing just t, the elapsed time. Okay. I was going to say something. Oh, the movie Hidden Figures. What they're trying to do, the whole drama of that was trying to figure out where a spacecraft would be. I believe it was when they start re-entry. And would John Glenn's space capsule, his Mercury capsule, where would it land and would it be safe? And so he had the women double check all the figures for him, and that's a real, I'm reading the book Hidden Figures right now, actually. It's a real story. It's not a fiction. It's a real story, and they really did this for John Glenn, and they checked his numbers, and basically they were doing a lot of distance triangles and a lot of distance rectangles for John Glenn's space capsule. Except it's very difficult to do in space, and you have to do a zillion of them because the velocity of the spacecraft is changing very rapidly, especially when it's on launch or when it's in re-entry. So, but it's basically all distance triangles and distance rectangles. Raise your hand if you've had calculus class. Bunch of yous. All right. For the rest of you, You know what we just did? We just did visual calculus. We just did calculus. You guys that were in calculus class, this is integration. You recognize it? You recognize the integration? You guys that were in calculus? Yeah, so the rest of you that didn't have calculus, you did calculus today. So you can call your, if you have an engineering major for a friend and they're really annoying, you can tell them, yeah, I just did some calculus today. It was easy. You know, or tell your parents, whoa, I did some calculus in my physical science class today. So yeah, that's what this is. Now, raise your hand if you would like to dismiss early today. I don't see everybody raising their hands, but okay, no, we'll just keep going here. Nobody, no, we'll dismiss early. Raise your hand if this is your last class of the week. Yay. All right. I want you to finish reading chapter 1. And also, I'm going to have another assignment for you, maybe a little bit bigger, to work on due Tuesday. I'll have that ready for you by lunchtime tomorrow, if not sooner. All right? If you want to double check anything about your iClipper, you can come on up to the front. Yeah, fire ahead.
I don't understand why we changed the formula to this.
1/2 AT squared.
Yeah, I don't get how we got here.
1/2 base times height.
I understand, but I just don't understand why this is squared because it doesn't.
Oh, you missed one of the. Let me stop the. Where's my? Here we go. Let me stop.